Fischer Esterification. We're going to prepare isopentyl acetate. Now the reaction for Fischer esterification is you take an acid plus an alcohol and you need an acid catalyst, and this is an example of nucleophilic acyl substitution where again your nucleophile is going to attack and your leaving group is going to leave, again in our short version of this reaction, and you will make the ester plus water is condensed out. Again, this is an equilibrium reaction, and as an equilibrium reaction this obeys Le Chatelier's principle. And we can control the direction of the equilibrium by controlling the amount of water that is present. So again, we're going to control the equilibrium by the water concentration. Okay, so concentrated acids would mean that your water concentration is low, and we're going to favor esterification. And if you have dilute acid, then that means your water concentration is high and you're going to favor hydrolysis. That is, you're going to favor the reactants in the direction as we have it written. Okay, so again, what we're going to do today is prepare isopentyl acetate. So our overall reaction is acetic acid plus our isopentyl alcohol, so 1, 2, 3, 4 carbons with a branch at the end, so 5 carbons total, so isopentyl alcohol. And again, this is an equilibrium reaction, and we require an acid catalyst, and we're going to make the isopentyl acetate, again, plus water. It's a condensation, and again, acetic acid, our isopentyl alcohol, and we're going to make our isopentyl acetate as the ester. And again, this requires the acid catalyst. So this requires, again, an acid catalyst. And as a catalyst, it's consumed and then regenerated. Okay, so again, that's our overall reaction. Procedure, I'm going to take 5 mils of 17 molar acetic acid and 4 mils of the isopentyl alcohol, and I'm going to use 3 drops of sulfuric acid. Again, a concentrated acid. I'm not going to introduce water to the system because that would help drive the equilibrium back toward the reactants. I want to do everything to keep water out of the system and favor the esterification toward the products. Okay, so my procedure, I'm going to take the 5 mils of acetic acid, the isopentyl alcohol, a few drops of sulfuric acid, a couple of boiling chips, and I'm going to put it in a reflux apparatus. Now, a reflux apparatus, this looks like a simple distillation apparatus to start with. You've got a ring clamp and a heating mantle and a round bottom flask. So your heating mantle, of course, plugs into a variac. Okay, and you have a round bottom flask, and you clamp that round bottom flask very well. Okay, so again, this needs to be the support for your apparatus, and it's very important that you have a boiling chip. For safety concerns, and again, this clamp is extremely important, and again, depending on the prep size, you can choose what size round bottom flask. We're going to use a 50 ml round bottom flask. Okay, so that's how you'd set up a simple distillation. There's nothing different there. Okay, what we're going to do is we're going to add a reflux condenser. So we're going to take our condenser that we've been using to condense in our simple distillations and our fractional distillations and just turn it upside on its side. And again, you're going to have water that's going to flow in the bottom. So water in at the bottom and water out at the top. And again, this keeps the condenser full. If you went the other direction, it could drain out the bottom here. So this way, you can keep the water flow very low and the water goes in the bottom. The coldest part is going to be at the bottom, and then the water goes out the top. And what you're going to see here is the liquid, when it begins to boil, the vapors are going to rise up, and they're going to rise up, and when they hit this cold jacket of the condenser, they're going to, again, condense and fall back in. So basically, a reflux will allow you to heat something almost indefinitely with no solvent loss. So this is a reflux apparatus. And you can put another clamp right here, but it seems to do all right like that. All right, I will apologize for in the video. I guess my camera angle alignment got bumped right before I started filming, and most of the video is nearly cut off at the top at the very beginning of the video, but that does get better. When I get ready to shut down the apparatus, you can see a pretty good shot of the whole apparatus. Again, you've done this before, seen it with the simple distillation up to this point. And then all we do is just stick a condenser on the top and turn on the water, water in the bottom and water out the top. Okay, mechanism. Mechanism, like anytime we use a acid catalyst, generally what we're doing is we're protonating the carbonyl to make this carbon more electrophilic, susceptible to nucleophilic attack. So that's going to be our first step here, is we are going to protonate the carbonyl with our sulfuric acid. Okay, now every step is an equilibrium if the overall reaction is an equilibrium. Now I can draw a second resonance form for this, where again I bring this electron pair out and I have the positive charge on the carbon. I'm going to leave this Lewis structure and not draw the other resonance form. Okay, so now my alcohol is going to come in and attack. So again, this is my isopentyl alcohol, and I'm going to attack the carbonyl. Okay, and electron pair is going to go out to that oxygen. Now again, every step has to be in equilibrium. Now we want to keep up with our protons. Here is the proton that was on the alcohol, and it's still there. So this proton is still there, so it's going to carry a positive charge. Now, this is not a good leaving group. Hydroxide would be a very poor leaving group, but if we do a proton transfer, then we can have water as our leaving group, and that would make a good leaving group. So I'm losing a proton and I'm gaining a proton. I'm moving the proton internally if you want to do it intramolecular. Okay, so here's the oxygen of the original carbonyl. Excuse me. I just protonated this oxygen to give me my oxonium. Here is the oxygen from the alcohol. Okay. Now this is poised to leave as water, so here's our important step. That electron pair comes in and the water leaves. That leaves us with a protonated carbonyl. Okay. And our last step here, I'm going to lose this catalytic proton. That's the proton I put on in the beginning. Okay, and in the last step here, I'm going to lose that and get my final product. And of course we get water with the loss here. Now, if you want to do the hydrolysis, do the mechanism in reverse. The first thing you would do would be to protonate the carbonyl, and then you would have water come in and attack, and then you would have, again, a proton transfer, okay? And then you would have the alcohol leave. So, again, high water concentration, you're going to go toward hydrolysis. Low water concentration, you're going to prefer esterification. There are lots of different esters that you can make. Isopentyl acetate is our ester from banana, and I'm sorry I left off an L right there, isopentyl acetate. Old nomenclature, this was isoamyl acetate. There are other esters that you can make with various odors or flavors. And I'm just going to give you a few of them here, and we'll work on a little bit of nomenclature. This is isobutyl formate. It's made from formic acid and isobutyl alcohol. So isobutyl formate. This is raspberry. Okay. Again, we've seen some acetate esters. I'm not going to redo the isopentyl acetate as banana. But here's one for you, octyl acetate, so 2, 4, 6, 8. So this would be octyl acetate. This you find in orange, it's a component of orange. Propyl acetate, this is a component of pear. Benzyl acetate, now make a distinction between the phenyl group and the benzyl group. Just the benzene ring alone attached to something is the phenyl group. If you have an extra CH2 here, this is the benzyl group. So this is benzyl acetate. And this is peach. Let's go up to 3 carbons. So 1, 2, 3 carbons in my carboxylic acid. And we'll do the isobutyl propionate. This is your rum flavor. And there are some butanoate esters that I would suggest not making them in the lab because butanoic acid or butyric acid by common nomenclature stinks pretty bad. So if you're going to start this reaction with a carboxylic acid that smells pretty bad, this is one, okay? This is your methyl butyrate or butanoate if you're doing common or doing IUPAC nomenclature. And I'm sorry, that messed up right there. So butyrate. And this is an apple. Again, a component. Ethyl butyrate or butanoate. This is a component of mango. And if we put a methyl, alpha methyl, okay, so what I've got here is methyl for the ester, alpha methyl butanoate. So I will just skip that name. This is your pineapple. So notice the difference between apple and pineapple is just this extra carbon right here, okay? And let's give you wintergreen is methyl salicylate. So salicylic acid with the methyl ester gives you methyl salicylate. And I will give you a thioester. Methyl thiobutyrate, this is your strawberry. So again, sorry, this is wintergreen, your methyl salicylate. And this is your methyl thiobutyrate. And this is your strawberry. Okay, just to give you an introduction to some nomenclature and esters. They have quite pleasant odors. Again, some of the starting materials might not be so pleasant. And again, I'm going to go through the lab and we will calculate our theoretical yield and determine our actual yield and then calculate our percent yield when we're finished with the experiment. Okay, we're ready to do the ester synthesis. This is a 5-4-3 procedure. I'm going to have 5 mils of glacial acetic acid. It's 4 mils of the isopentyl alcohol. Old nomenclature was isoamyl alcohol. We're going to do a reflux. And this looks like a simple distillation apparatus to begin with. Again, you want that ring clamp fairly tight. I'm going to take my round bottom flask, a couple of boiling chips, okay, heating mantle, got my variac plugged in, is 5 mils of our acetic acid, glacial acetic acid, 17 molar. Four mils of our isopentyl alcohol. Three drops of our sulfuric acid. We'll turn on the variac, and with a reflux, you put the condenser on top of the round bottom. Again, make sure you got a really good seal there. Okay. Water in the bottom and out the top. And turn it on gently. This hasn't been opened in a long time, so no telling what's going to come out of the pipe. Again, adjust the flow. If you turn it up too much, it could pop a hose off. This is your skin. This is your skin on sulfuric acid. And it just takes a couple of seconds for you to get a 2nd degree burn, and a couple of minutes you'll have a 3rd degree burn. And I would say my sulfuric acid is not too strong. It's been sitting on the shelf for a long time. But I think you get the idea. So again, that's your skin on sulfuric acid. So be careful. Okay, I want to get the mass of my empty vial. Turn on the balance. .093. And we'll call it 25.094. Okay, we've been refluxing for about an hour, and I think I'm ready to stop this. So I'm going to turn off my variac. I'm going to lower my heating mantle. I'll move my heating mantle out of the way, and I'm going to turn off my water. Make sure my water is turned off. Remove my condenser. Drain the water out. Try not to make a mess in the hood. Recall that the stopcock needs to be, again, perpendicular to the separatory funnel if you want it off, okay? If you want it to drain, you put it in parallel, okay? You want to make sure that your ring clamp fits your separatory funnel. Again, that you've got a little bit of grease on the stopcock, sorry, the stopper, and that your stopcock is functioning correctly. I usually test it to make sure it's not going to leak. Okay, so this is our product, and I'm going to carefully transfer it to the separatory funnel. Again, my separatory funnel is closed. I'm going to rinse this with a little water. Again, it doesn't have to be exact, you're just doing a rinse step here. So we've done this before to invert and vent. And again, don't shake too vigorously. And I hope you can see that you have two layers in there. And we're going to set it up here. And I'm going to drain off this lower aqueous layer. Okay, again, when you drain, you want to make sure you remove the stopper first. And then open up the stopcock. And again, this will blow out the sides, so you want to make sure you're down inside your beaker or your Erlenmeyer. And again, you got to be really careful about stopping. So you want to stop this right at the interface. Try not to get any of your product to drain off. Okay. I'm going to get 10 mils of my bicarbonate. Again, wash volumes don't have to be critical. There's 9 mils. I'm going to go with that. Now again, this is the bicarb. It could possibly generate some gas. So you want to make sure you vent this. Again, finger over the stopper, invert, open the stopcock, don't point it at you. I shouldn't have been talking, you may have heard that vent. I hope you heard that one. Again, I'm going to drain off that lower layer. Remove the stopper, open the stopcock. Lastly, I'm going to rinse with my sodium chloride, wash with my sodium chloride.
Again, approximately 10 mils. Volume's not that critical. Okay, I'm going to drain my product into my clean, dry Erlenmeyer. And I'm going to put a drying agent in here. So I'm going to add a little drying agent, calcium chloride. There are other drying agents that you can use. And again, you can filter these, but I tend to lose a lot of product in the filter paper. I'm going to carefully decant this into my vial. Okay, that looks pretty good. .252. 28.252, and the only thing you're missing is this very intense banana smell. It is so strong. Okay, so there's my product.
Okay, we need to calculate the theoretical yield and the percent yield for our experiment. Again, we're taking acetic acid. I have 5 mils. It is 17 molar. I'm reacting that with my isopentyl alcohol. I have 4 mils of it. Its density is 0.81 grams per mil. And again, this is an equilibrium reaction, and I'll be making the isopentyl acetate plus water as our byproduct. So again, our actual yield, we have to get this from the experiment. Okay, so let's calculate how many moles of each reagent and determine our limiting reagent. The acetic acid should be in excess, and the isopentyl alcohol is probably our limiting reagent. So again, for our acetic acid, the easiest way to calculate the moles is to use the concentration. So I have 5 mils. Let me go ahead and convert that to liters. 0.05 liters times 17 moles per liter. So let me do that calculation. 0.005 times 17 gives me 85 millimoles. So 0.085 moles. For my isopentyl alcohol, again, this is my acetic acid. For the isopentyl alcohol, I've got 4 mils. The density is 0.81 grams per mil, so mils can cancel. I have grams. I'm going to need the molecular weight for the isopentyl alcohol. It's 88. I just had to look that up. 88 grams per mole. Again, we can calculate that very easily. Okay, and now calculate the moles. 4 times 0.81 divided by 88 is equal to 36 millimoles, 37 millimoles. 0.037 moles, so 37 millimoles. So you can see 85 millimoles is the larger value. The acetic acid is in excess, and the isopentyl alcohol is the limiting reagent. Let's calculate the theoretical yield. So I have 4 mils as my limiting reagent. My density is 0.81 grams per mil. The molecular weight was 88 grams per mole. I have 1 mole of the ester for each mole of the starting material, the alcohol. And I need the molecular weight for my final product. It is 130 grams per mole. Again, we can add that up. I'm just looking at it in a table. Okay, milliliters cancel, grams of reactant cancel, mole of reactant cancel, mole of product cancels, and I've got grams of my product for my theoretical yield. So let's calculate this out. 4 times 0.81 divided by 88 times 130 gives me 4.79 grams for my theoretical yield. The percent yield is actual over theoretical times 100. For my actual yield, the mass of the vial plus the product was 28.252 grams. The empty vial was 25.094. And so 28.252 minus 25.094 gives me 3.158. We'll say 3.16 grams. And so my percent yield is 3.16 grams over 4.79 grams. So 4.79 gives me 66%. So 65.9% times 100 gives me 65.9% for my percent yield. Excuse me. For my percent yield. Not too bad. Okay, thank you.